In the last video, I went over how ionic bonding energy is involved, how it requires energy to break the attraction between the lithium nucleus and its valence electron, requiring energy to go into the system. I went over how to form the anion. You need the attraction forms between the nucleus and the electrons. Since attraction is forming, it releases energy. And the crystal lattice, because of how stable it is, requires much less energy to hold itself together, and as a result, energy is released from the system. In this means, if you remember from earlier, when we talked about bonding, we said that bonds were attraction between atoms. And in this case, ions. And so with that being said, bonds form when there's an attraction. So forming bonds is an attraction. So, and forming that attraction releases energy due to being more stable. Breaking bonds is simply breaking attraction and it requires energy. So again, let's think of some magnets. If I have magnets, I can bring my magnets close to each other. I don't have to have them touching. I can bring them close to each other and they'll attract. And that attraction releases energy. How do I know this? Because I hear them click together, and so that click is the energy being released. If it were absorbing energy, then when they came together, I wouldn't hear any noise. And to go along with that, to break the bonds, to separate the magnets, we have to put energy into the system. There isn't any sound that comes out when you pull the magnets apart. And that's because you need to put energy in to separate that attraction, to break that attraction. And so when we were talking about our energy, we were talking about the different types. I'm going to clean this up a little bit because I'm going to give us a picture way to look at it for some of us that are visual. And so to review what we went over, we said that we had to form our ions, and after forming our ions, then the ions would form the compound in the crystal lattice. And so to do this, we're going to look at this graphically. And so with my graph, I'm going to keep it very, very simple. You need to label your 0, which is your axis, and you need to label this as energy. And so, in order to form my cation, and this will be true for any cation, it requires energy to be put into the system. And we said that that energy was called ionization energy. We need to make sure we label this ionization energy as our cation. So it could be any cation, whatever we're talking about in any compound. Just make sure you write the ionic formula, meaning the symbol with its charge. So for example, if this were beryllium, then it would be Be plus 2. If it were aluminum, it would be Al plus 3 that you would label above the ionization energy bar. Then we have our anion, and since our anion is forming an attraction, it's going to release energy from the system. And we said this was called electron affinity or electron attraction. It's less energy because when we look at our numbers, it's less. You don't have to do these numbers exactly on a measured scale, but it should be less energy that's released because it was less energy in my numbers. And again, you need to label this with the ion formula. So in this case, this is fluorine -1. So that's the energy required to form the anion fluorine -1. Finally, we have our lattice energy. And our lattice energy is a lot more energy than the other two. And so again, it doesn't have to be perfect, but I should be able to tell that it is definitely a larger amount of energy than the others. And so this was our lattice energy. This is the energy that's released when my ionic compound forms. So that means we're going to label this with the ionic compound. This is just an easy picture way to see it. It'll be the same format every time. You'll label the ionization energy and your cation formula. You'll label the electron affinity or electron attraction as the anion, and you'll label the lattice energy as the ionic compound.